Hi guys, Dr. Gillard here. It is Tuesday. It's time for our second endocrinology lecture. It's the spring of 2021. And here we go, little biochemistry stuff. So I hope you remember glycolysis. Oh, let me turn this on too. Hope you remember your glycolysis, gluconeogenesis, and the Krebs cycle. You need that for boards. So I know you do, but maybe you don't. So good time to review. So what is gluconeogenesis? What is the deal with this thing? Well, it's normally turned on when your blood glucose levels go low, like fasting. Even overnight fast will crank up your cortisol levels in the morning. And the job of gluconeogenesis is to make sure that you always have sufficient blood glucose levels so you don't crash. Remember the brain cells and red blood cells, and there's other cells too that they can't run glycolysis. They can't make their own glucose. So they rely on blood glucose to stay alive, and you definitely don't want your brain cells dying, right? So it's a very important process. What stimulates it? What drives gluconeogenesis? Well, in general, you could say it's stimulated or driven by hormones, specifically diabetogenic hormones, such as glucagon, growth hormone, epinephrine. They can all drive it. We're concerned with cortisol because we're leading into Cushing syndrome, which we will start here in a little while. So cortisol, you could say it indirectly stimulates it by creating fuel for it. So it's driven by amino acids and glycerol. Are probably the two big ones. We'll look at another one too. How does it work? Well, you need fuel for it. So to make glucose, you have to, you could say, we all learned glycolysis, right? That's probably the first thing you ever learned. And then you kind of semi-learned the Krebs cycle. But it's basically running glycolysis backwards with a few caveats, because there's a couple enzymes that don't go both ways. They can't, you can't run backwards through them. But now you can't, in glycolysis, you start with glucose, right? You trap glucose in the cell by sticking a phosphate on it. So you can't start with glucose because we're trying to make glucose. So we have different starting molecules, which come from amino acids. Glycerol and lactate are the big ones again. And yeah, the problem is those irreversible steps. So who are the irreversible steps? That's a nice, easy softball biochemistry question that I'm sure you've had to memorize these before. So the very first enzyme in glycolysis, hexokinase, which is in many different, like in your muscle tissue, it's in many tissues in the body. And then glucokinase, where's that one? You guys remember that from biochemistry? These are isozymes, by the way. That's that first step. This is what traps glucose inside the cell so it can't get out. This one is in the liver and in the beta cells of the pancreas. This is a one-way enzyme. It has to be because you don't want glucose getting out of the cell, so it's a one-way enzyme. The third step, phosphofructokinase 1, is another irreversible enzyme. It just goes one way. And then the very last step, pyruvate kinase, the making of pyruvate, which is the end phase of glycolysis. So in order to create glycolysis or gluconeogenesis, in order to make glucose, we need to replace these enzymes. And then actually a couple more too, but for sure we need to replace those. Who do we replace them with? Well, glucose-6 phosphatase is the final step. That's the last enzyme needed to make a molecule of glucose. The third to the last step is fructose 1,6 bis phosphatase. And then the second step in this process, kind of depending where you're starting, is PEP carboxykinase or phosphoenopyruvate carboxykinase. And that's assuming that you're starting with oxaloacetate. That's the big if you had to pick one fuel that drives gluconeogenesis, it's oxaloacetate, or OAA. What is that? What do you know about that, oxaloacetate? Well, that's the end product of the Krebs cycle, aka TCA cycle, right? And that can be converted and run into gluconeogenesis, as we'll see. And then pyruvate carboxylase is the very first step, assuming you're starting with pyruvate. So now it's getting a little foggy for you, right? We need to look at this. Oh my gosh, you're thinking, now it's not that bad. I don't think it's that bad anyway, because I've been learning this since high school. I've learned glycolysis, and so it's just running it backwards except for these new enzymes. So here's the deal right down here. So the end of glycolysis, of creating energy from glucose, is pyruvate. So in order to run gluconeogenesis, you have to go backwards through this. So the starting molecule could be pyruvate, and you can do two things with it. You can run it through the Krebs cycle and create oxaloacetate. And remember, all those enzymes of the Krebs cycle makes oxaloacetate. Or let's say you don't need energy, because you'll make a lot of energy through the Krebs cycle. You don't need energy, you just need glucose. You can directly convert it into oxaloacetate, but you need a new enzyme that you're probably not familiar with, and that's pyruvate carboxylase. Pyruvate carboxylase. So you should know the two options. If you're a pyruvate molecule, how do you get to oxaloacetate so we can start the process of gluconeogenesis? Well, there's two options. You can go straight into it via pyruvate carboxylase, sometimes it's just called PC. Another PC enzyme, that's all we need. Or you can run it through the whole 9 yards of the Krebs cycle and make oxaloacetate. The oxaloacetate is, remember I said, if there's one starting molecule for gluconeogenesis, it's oxaloacetate. It can be acted on by PEP carboxykinase, or phosphoenolpyruvate. It says PEP. Everybody just calls it PEP, but it's phosphoenolpyruvate. And that converts it into the second to the last molecule here in this glycolysis, which is phosphoenolpyruvate. It's PEP. It's actually two molecules. Well, no, we don't. I won't even go down that. Right? And then enolase is a two-way enzyme, so you can run it back to here. Phosphoglycerol mutase is a two-way enzyme, so you can go back. And you can go back and back and back and back. And you can go back through here. But you're going to get stuck right here, because phosphofructose kinase 1 is a one-way enzyme. So now you're going to have to take fructose 1,6-bisphosphate, and you're going to have to use an enzyme called fructose 1,6-bisphosphatase, and that converts it into fructose 6-phosphate. And then we can use that same glycolytic enzyme, phosphoglucose isomerase, to convert back to glucose 6-phosphate. And then we're stuck again, because the hexokinase or glucokinase, which depending on where you are, that's a one-way enzyme. So we have to take glucose 6-phosphate and use a new enzyme called glucose 6-phosphatase, and that will create glucose, our desired. That's the whole point of this whole thing, is to create glucose. See how that works? All right, so be ready with it. I'm probably not going to ask you all these intermediate steps. You've had that in biochemistry, but I'm definitely going to ask you these. You should definitely know pyruvate carboxylase, PEP carboxykinase, and you should know a little bit about this. And you probably, for the boards, you're going to have to know all these steps and enzymes anyway. And so glucose 6-phosphatase is the last step, the final step to make glucose. That's an easy question. Fructose 1,6-bisphosphate, not quite as easy of a question to ask, not as easy as glucose 6-phosphatase, but know them. Okay, what does it use to make glucose? So what are the starting molecules? Well, I just kind of said, but let's keep talking about it, because there's more stuff. So we said the great starting molecule is oxaloacetate, which is the final product of the Krebs cycle. But what do we use to make oxaloacetate? Well, beside the Krebs cycle, there's other ways we can make it. Remember we said pyruvate can be converted directly into oxaloacetate. Most amino acid except leucine and lysine, all the amino acids except leucine and lysine can be run through the Krebs cycle. Some of them don't run through the Krebs cycle, but most of them run through the Krebs cycle and can be converted into intermediates of the Krebs cycle to make oxaloacetate. See how that works? Lactate is converted into pyruvate, right? That's anaerobic glycolysis, makes lactate, or lactic acid, it's aka for that. So that, like muscles working and making lactic acid, you can take that lactic acid and convert it into pyruvate, and then you can convert it right into oxaloacetate by either running it through the Krebs cycle or converting it directly into oxaloacetate. Note, glycerol, which is the breakdown of fat. What's fat made of? Glycerol and fatty acids. Glycerol cannot be converted directly into oxaloacetate. That's converted into one of the gluconeogenesis intermediates itself. And let's talk about glycerol for a minute. It's derived from the breakdown of fat. What is the breakdown of fat? Lipolysis or lipolysis. That's the breakdown of fat. And what are the breakdown products of lipolysis? These are softball questions. Can't miss these. Glycerol, fatty acids. Glycerol is converted into one of the glycolysis intermediates, which is also a gluconeogenesis intermediate. It's called glyceraldehyde 3-phosphate. I'll show you the pathway in a second. But remember, fatty acids are also converted. Fat is made of glycerol and fatty acids. What about fatty acids? Can we run those through the Krebs cycle? The answer is no. They can be used to make ketone bodies, and ketone bodies is kind of a form of glucose that you can use. I won't go down that pathway though. Lactate. You can also take lactic acid, and here's the pathway right here. Alanine also goes through this pathway, but it runs through something called the Cori cycle. And we don't have to worry about all the pathways and all the intermediates of that, but it's run through the Cori cycle, and it is converted into pyruvate. And then the same thing with pyruvate. You can run it through the Krebs cycle, citrate, isocitrate, alpha-ketoglutarate, succinyl-CoA, succinate, fumarate, malase, or malate. And then there's our target, OAA, oxaloacetate. And once you got oxaloacetate, we know what we can do with that. PEP carboxykinase can convert it into PEP, and then we're off to the races, right? Running backwards through glycolysis. All right. Or did I say we can convert it directly into oxaloacetate? Yeah, by PC, pyruvate carboxylase. Definitely know these little steps right here. Oh my God, looks scary, doesn't it? But it, what else can we use as a starting molecule? Well, oxaloacetate is still our starting molecule, but we can use, as I said before, almost every single amino acid can be run through the Krebs cycle, or used to create pyruvate or acetyl-CoA, and turned into oxaloacetate. So I won't go through all of these, but you can just see a whole bunch of them. Acetyl-CoA can't be converted directly into oxaloacetate though. If you take like tryptophan or tyrosine and you convert that into acetyl-CoA, it's got to go through the citric acid cycle to make oxaloacetate. But then we know the rest of the pathway. Oxaloacetate can go right through gluconeogenesis. Okay. Here's leucine and lysine. Now this author actually screwed this up. This cannot be used to run through. You can't make acetyl-CoA with this. Leucine and lysine is used to make ketone bodies. They're ketogenic. They're not gluconeogenic. All these other enzymes, because you can ultimately make glucose with them, these are the gluconeogenic amino acids. But not leucine and lysine. Those are ketogenic. They're used, you can make ketone bodies, which is another form of fasting glucose. All right, you got it? Also interesting to see alanine, glycine, serine, cysteine, and some other tryptophan, threonine. They can all be used to can be converted into pyruvate, and therefore they have a choice. They can be converted by PC directly into oxoalloacetate, or they have to go through the entire Krebs cycle. Are we good? All right. Here's fats. Just take a look at what happens to fats. So cholesterol stimulates lipolysis, and a fat is broken down into glycerol and fatty acids. Glycerol is converted by glycerol kinase into glycerol 3-phosphate. Glycerol 3-phosphate is converted via glycerol 3-phosphate dehydrogenase into dihydroxyacetone phosphate. Right? That's one of our members, and then it can just run right backwards. It still needs these new enzymes, but we can make glucose directly out of glycerol. Fatty acids, no, but we can, besides making ketone bodies, we can burn fat. We won't talk about the process, but we can use fatty acids and I believe it's oxidize them to create ATP and NADH, and we can use this energy to drive the Krebs cycle. So in a way, I mean, the fatty acids aren't ultimately going to end up as glucose, but we can use the energy derived through oxidation of them. I won't test you on oxidation. I mean, if it's not on the slides, I'm not going to test you anyway, right? It's got to be on the slides, but somebody can let me know if it's oxidized or reduced. I can't remember which one. Where do the amino acids come from? That's a nice, easy question. Well, the muscle, of course. So the process of catabolism. Cortisol binds to muscle cells, and it causes the muscle to break down and release the free amino acids. Right? The amino acids get into the bloodstream, they float around, and they end up in the liver where most of this process of gluconeogenesis occurs. And many of them are converted into intermediates of the Krebs cycle or acetyl-CoA, and they're actually ultimately converted into oxaloacetate, which is the major precursor for gluconeogenesis. Right there, that doesn't look as scary, right? Looking at all the just amino acids, and we just went over that, so I'm not going to go over that again. Glycerol, where does that come from? That comes from lipolysis, as I said, but here it's in stone, so I can ask you a question on it. Cortisol binds to fat cells, and it stimulates lipolysis. They're broken down into glycerol and fatty acids. Right? And we just said fatty acids can't be converted into glucose via gluconeogenesis, but they can be burned. I was right. It was oxidation. They can be burned. They can be oxidized via beta oxidation, which creates energy that can be used to drive gluconeogenesis as well as the Krebs cycle. And that energy is ATP, NADH, and FAD, mainly ATP. But they can't be used. That's the question. They can't be used. And I'll try to tell you, I'll try to sell you that they can be used, and they can't. Fatty acids can't be used to make glucose. And the glycerol, we've already said that, it turns into dihydroxyacetone phosphate, which is a member of glycolysis, the glycolytic pathway, as well as the gluconeogenic pathway. Right, why do I have this in here? We've really covered all of this. Did we go through glycerol, how it's converted? I think we did, didn't we? Glycerol kinase. Yeah, we did this already, so could probably take that slide out. Last slide on this, thank goodness. I know many of you are going, oh, thank goodness. This is a really cool slide. And we can talk about some other functions. Cortisol's effect on the muscle is not only to release proteins, to break down proteins into amino acids. It also does some other cool things. It decreases protein synthesis, which requires amino acids. So you don't want to, you want to release amino acids in the bloodstream. You don't want to use them to build, like if you're a bodybuilder, you can't build muscle when you're starving because the cortisol will shut down protein synthesis. It also makes the muscle cells reject glucose. not completely, because they need some glucose to stay alive, but it makes them use it very sparingly, so decreased glucose utilization. Same with fat cells. All the cells, many of the cells in the body won't use glucose when cortisol's around, because we're trying to put amino acids and glycerol into the bloodstream to make glucose to keep the human alive, whose cortisol thinks the human's dying, and maybe the human is, and it needs glucose. And to that end, insulin is also resistant, because we know insulin, insulin will stimulate GLUT4 transporters, which will grab glucose and pull it inside the muscle cell. Well, we want to keep the brain alive and the liver and the vital organs alive. So we don't need glucose getting sucked into muscle cells. A little bit still happens to keep it alive, but it gets real stingy. Same with fat. So it becomes insensitive, or has decreased sensitivity to insulin, adipocytes, as well as muscle cells. See how that works? And then when the amino acids go into the liver, it drives gluconeogenesis. It also increases the production of the enzymes for the Krebs cycle and gluconeogenesis. And it increases the activity of the enzymes as well. And plus it stimulates glycogen storage, or glycogen synthesis. We'll try to store a little bit if there's enough amino acids around. Alright, I think that is about all I wanted to say, so play that back, because I'm going to hit you on this. You got to know this stuff. So, alright, but let's switch gears, thank goodness. Cushing syndrome and Cushing's disease. So let's talk about Cushing syndrome. Again, Cushing syndrome, the S means something is causing the overproduction of cortisol in the body. And it could be many things, ACTH-dependent or ACTH-independent, but there's many causes. But Cushing syndrome doesn't care. All it cares is that something is over-secreting cortisol. It's also called hypercortisolism. It's the opposite of the adrenal insufficiencies, primary and secondary adrenal insufficiencies. You don't secrete enough cortisol. Now you're secreting too much cortisol. It's rare, this one. I usually don't even talk about diseases much rarer than Marfan's syndrome. Marfan's is 0.01. This one's 0.001. It's quite a rare disease. You would think it's so popular, the boards love this thing, you would think it's more common, but it's rare. You'll probably never see a case of it. I've never seen a case of it in my career. Yep. But I have actually seen, it's a little more common, I have seen prednisone-induced Cushing syndrome, or iatrogenic Cushing syndrome. That you might run into. I forgot to get the prevalence on that, but that's much more common. Anyway, it occurs when something causes a significant rise in glucocorticoid levels. In other words, something is over-secreting cortisol. And it's no joke when it occurs, because it can be fatal. 5-year survival rate is about 50% if it's not treated, and it can be successfully treated. There's 2 subcategories of Cushing syndrome. ACTH-dependent means ACTH is driving the condition. Nothing wrong with adrenal glands. ACTH-independent means the adrenal glands are screwed up and they don't care about ACTH. It's the adrenal glands is over-secreting cortisol, independent of ACTH. ACTH doesn't have anything to do with it. Some people break it down into exogenous Cushing's disease from prolonged use of corticosteroids and endogenous Cushing's disease, which is from tumors, and we'll look at all that stuff in a minute. So that's another possible breakdown. So let's look at ACTH-dependent causes first. So that means that this type of Cushing syndrome depends on the oversecretion of ACTH. Alright, so ACTH-dependent causes of Cushing syndrome. This disease is driven by the overproduction of ACTH, or POMC-ACTH. So that means that there's nothing wrong with the adrenal gland. The adrenal gland's fine. There's something wrong with the pituitary. And it's usually a corticotroph tumor, as we'll see. So the number one cause the number one cause of ACTH-dependent Cushing syndrome and the number one cause of Cushing syndrome, just period, is this, aside for iatrogenic, man-made overuse of corticosteroids. But Cushing's disease, here's the good question. Cushing's disease is the number one cause of Cushing syndrome. There's the question. True or false? Cushing's disease is the number one cause of Cushing syndrome. That's true. What does it cause? What is Cushing's disease caused by? And that's also the number one cause of ACTH-dependent Cushing syndrome. What is it caused by? It's typically a tumor, an adenoma, which is a tumor filled with glands that secrete stuff. And this adenoma is full of corticotroph cells, and it usually lives in the anterior pituitary. So you basically have a tumor of corticotroph cells cranking out ACTH, or POMCs converted to ACTH. And yep, that's it. If you have high levels of ACTH, it's going to drive the pituitary or the adrenal gland like crazy. The adrenal gland is going to secrete tons of cortisol and tons of the adrenal androgens as well, right? Because ACTH stimulates the release of cortisol and the adrenal androgens like DHEA or androstenedione, DHES. Those are the adrenal androgens. Okay, so pituitary tumor, number one cause. There's some other less common causes. You can have an ectopic ACTH syndrome. So you have a tumor like in the pancreas that is secreting ACTH. These are really rare, but it can happen. You could also have, and that's an ectopia, right? It's an ectopic source of ACTH. You can also have a tumor in the paraventricular nuclei of the hypothalamus. Remember, that's where the parvocellular neurons live. So you can have an adenoma made of parvocellular neurons which oversecretes corticotropic releasing hormone, or CRH. And we know that one comes down and it binds to the corticotroph cells and stimulates them to produce ACTH. So that's a third cause. And it could, it's ectopia, so it could also be maybe that pancreatic tumor that secretes CRH. Because as long as the CRH gets in the bloodstream, it'll hit the anterior pituitary. So, so those are the causes, really rare. It's that anterior pituitary tumor is the main cause of this. And yeah, the adrenal androgens, as I said, they're oversecreted too. Because if ACTH is coming out in globs way too much volume, it's going to stimulate cortisol and the adrenal androgens as well. And if you oversecrete the adrenal androgens, in males you're probably not going to notice that too much, but in females it causes virilization, or it gives females male characteristics, right? They start growing whiskers. And here's someone with this condition, and deepens their voice, and just like a kid going through puberty, getting 12 years old and becoming a man, they get acne, baldness, increased libido, increased muscle mass. All right, what about ACTH-independent causes? So if independent means there's nothing wrong with the AHP axis, there's no tumor in the pituitary, ACTH production is normal. It means that cortisol is being cranked out by the adrenal gland itself, or something else is cranking out cortisol independent of it being driven out by ACTH. So yep, so it has nothing to do with the overproduction of, or it has nothing to do with the overproduction of ACTH. And something is causing cortisol to be released from the adrenal gland. It's usually the adrenal gland itself that is the problem. And yeah, so what is the number one cause? It's a tumor, not in the pituitary this time. It's a tumor in the adrenal gland itself. And the tumor is usually an adenoma made of reticular cells, or fasciculata cells. Remember, fasciculata cells are the ones that make cortisol. So it's a fasciculata tumor, adrenal adenoma, and it's cranking out cortisol de novo all by itself. That's the number one cause. There's some rare causes, one called PNAD, I call it PPNAD, primary pigmented nodular adrenal cortical disease. Oh my goodness, I hope that won't be on board. It's super rare. Of the ACTH-independent causes, it represents only 2% of the pie. It does occur. And here's a child that it occurred in, and they had to take it out. This is the adrenal gland, and it's got these spots on it. So it's did I write that down somewhere? It's classified by these small pigmented nodules that are adenomas, and they secrete glucocorticoids, or they secrete the glucocorticoids. And the interesting thing with this, the adrenal gland, we'll talk more about this the next time as well, but the adrenal gland in these adrenal gland or adenomas, adrenal gland can be really big because it's working out and it's secreting tons of cortisol, so it gets big. But in PNOD, it doesn't get big. It might even be smaller than normal. And then, of course, it visually has these spots, and these spots are filled up with tumors that secrete cortisol. Okay, there's some other really rare causes, McHugh and Albright syndrome. We won't get into the mechanism. But the big one here is exogenous Cushing syndrome, or the prolonged use of exogenous glucocorticoids, usually above physiological levels. Like 20 milligrams is a common dose. And people have been on that for a couple years, and they can start getting a little cushiony looking. They get the moon face. They get the Homer Simpson belly, the pendulous abdomen. It's called truncal obesity is the medical word for that. Truncal obesity. And so exogenous Cushing syndrome. Sometimes it's called iatrogenic Cushing syndrome, meaning it's a man-made type of Cushing syndrome. So that's another cause of ACTH-independent Cushing's syndrome. Another cause, alcoholism. So some alcoholics, alcohol used in excess, and I'm talking about probably a case a day, and there's plenty of people in the country who, believe it or not, drink that much beer a day, a case a day. Some people drink tons of beer. They're not going to live very long, but they will. But that much alcohol will stimulate parvocellular neurons to do their thing, and that's release CRH. And and it doesn't matter if the cortisol can't shut this type of, it can't compete with alcohol, because normally if you over-secrete CRH, you'll over-secrete ACTH, and that causes the adrenal gland to over-secrete cortisol, and the cortisol will shut this mechanism down, but the alcohol overpowers it, and it just makes these parvocellular neurons super sensitive and just irritates them to the point they do their thing. They over-secrete CRH. And the double negative feedback system can't shut it down. Okay, we're good with that? All right. And that's enough for your brains. See y'all later.